Hello everyone and welcome to our webinar with the topic Benefits of Rigid Flex & Co. Impedance Control for Good Signal Integrity. First, I would like to introduce the speaker today. Mr. Andreas Schilp is a product manager in Würth Elektronik in the product area Flex Rigid Printed Circuit Boards. He will present the topic to you. My name is Dominik Walz. I am responsible for online marketing at Würth Elektronik, and I will host today's webinar. Before we start, I would like to point out that you are muted during this webinar, but you still have the opportunity to ask questions using the questions area. You find it at the right side of your screen in the webinar panel. We will be answering your questions in writing, but sometimes also during the presentation if it fits with the current content. At the end of the webinar, we will have a little questions and answer session. There we will answer a lot of questions too. I would like to test the question function with you now, so please type in where you are from, your local weather, and send your answer to me. I give you a short time. We are here in Niedernhall, Germany. The weather is cloudy and we have about 15 degrees. Okay, now I see the first answers. Sunny weather in Durham. There is somebody of France. In the Netherlands, it's sunny and about 18 degrees. So I see that the function is working right now. You are welcome to ask questions. Use the function. Just a short hint before we start. We will publish the presentation on our website after the webinar. You will receive the link per mail. Well, I think you'll have understood everything, so I give the word to Mr. Schilp and wish you a lot of fun with our webinar.
So good morning and welcome to the webinar. The topics for today are shown here. We will have a look to impedance and the circuit board. We will discuss about signal integrity, especially for flex rigid boards. We will learn about some design options with flex rigid. We'll have a look at the cooperative design flow, show some measurement equipment and also documentation of measurement results, and last a summary and question and answer session. So for high-speed signals, the need for a closer look to signal integrity is important, even for flex rigid boards. And we have a transmission line here in between a sender and a receiver, and this has an impact to the signal strength, the signal form, and the timing. An example is shown here with a TV screen and short line from an antenna, and if this line is not matching, we have of course an impact on the picture, as you can see on the right side. So the requirement for this transmission line comes from the specification of the interface, and in our case that's a printed circuit board as you can see here on the cross-sectional picture, showing a signal line and a reference layer below. So we know that a printed circuit board is not an optimal transfer medium, and the change of the information due to, for example, construction details, that means length and width of the conductor, and losses by ohmic capacitive and inductive resistances, and the characteristics of the used raw materials are changing the signal. Another point is due to the design and the routing changing, for example, the cross-sectional area of a connector, which means an impedance jump. Also, perhaps switching the reference layers, which is another impedance jump, and also reflections due to the use of plated through holes, as the cross-sectional area is changing again, and also there is a kind of antenna due to these plated through holes. So at that point it's an advantage to use micro wires, as there are no more antennas then, and the change in the cross-sectional area is smaller compared to standard plated through holes. Of course, the signal is also changed by crosstalk between conductors if they are routed parallel, for example, and also noise interference from external sources. So signal integrity and the PCB, we can see some core topics. On the right side you see a design of a flex rigid PCB, which is quite typical, with green rigid areas and some flexible areas in between. And another thing is that there is a flexible shielding foil integrated in the system. So this helps to avoid interference disturbing the signals. As you can see here, this is folded into the package, and using this extreme possibility of miniaturization, and at the same time having a shielding possibility in between the single modules, this is quite a nice option using flex rigid. Another important point is that using flex rigid there is a system advantage, as we have disappearance of connectors and cables, so the signal integrity is quite better compared to cable and connector solutions. Another small point is that using flexible material we have a really flat copper surface, and especially for high frequency signals this is another advantage. So the skin effect is very low compared to standard treatment, which is very rough. So the topics are impedance power matching, caring for the timing issues, and avoiding reflection as far as possible. This example shows a detail from a USB 3 design. We can see some differential pairs, and the shape is to match the timing. So the lengths of this differential bus should all be equal. So on the one side we have a sender, and on the other side a receiver, and in between is the circuit board. This could also be the output of a logical component, and on the other side the input of a logical component. and in between the circuit boards. So it's important to match the impedance requirements, in this case shown as a 50 ohms inductance value. So then there is an impedance matched PCB. So we have to work on the design. That means choose a special stack up and taking care for the routing and or layout. Let's have a look on a simple model. This is a single strip line with one reference layer shown on the left top side, and below that you can see the complex equation of the complex resistance. To make it a little bit easier, we assume that there is a loss-free transmission. That means R and G becoming 0, and so we have the complex resistance dependent on the inductance and the capacity. Transferring to the PCB and the model shown, that means that the inductance is mainly dependent on the length of the conductor on the one side, and on the other side the capacitor is important, which is mainly given by the length and the width of the conductor, the dielectric thickness, and the dielectric constant of this isolation layer. So all in all, this builds a capacitor, and these are the two main effects we have to regard. We have different possibilities for models we can use in PCB technology dependent on the layer configurations. For example, if we have only one layer available, we have to use surface coplanar construction, or if we have 2 layers available, we can use surface microstrip or embedded microstrip, and strip line needs minimum 3 layers. Regarding the track configurations, we can use single-ended transmission line or differential pair transmission lines. So how can we calculate impedance values? I don't want to go too much into detail, as this is already covered by another webinar which my colleague Philipp Reb held last year. But I want to show now the black values, which are covering mainly material and process issues, which could not be changed very much, but the red ones, these are covering design and layout routing issues, and we have to have a close look at these parameters. Now, what about the effects of these parameters? We can see that especially the drag width and the layer distance have a really strong impact or effect on the impedance values. The copper thickness and the dielectric constant, they are more or less, not with a high effect, but with a low or medium effect. Regarding the cross-sectional picture here, we can see the values again, and the drag width and the layer distance, they have on the one side a very strong impact on the impedance value, and on the other side they are we can use this in the layout, in the design, to match the impedance requirements. Now let's see some specialties with flex rigid technology. Compared to standard rigid boards, we have of course a very big material mix, so additional materials like flexible cores, adhesives, cover lays, bond plies, and things like that. So more complicated compared to rigid boards. This makes it difficult to also to documentate all the stack-ups and so on. The stack-up is different in the rigid area compared to the flexible area. In the picture on the left side we see a symmetrical strip line in the rigid area, and this converts to a surface strip line in the flexible area. Third point is we have a low dielectric constant for polyimide, which is a flexible material, and the main issue is the low thickness of the flexible dielectric. So for polyimide, a standard is 50 micron, and there are of course thicker polyimide films, but they are very expensive. So a solution to meet the requirements is to match the impedance values in the rigid and the flexible area. Doing this, we have to define a target impedance value coming from the specification of the interfaces. We have to choose impedance models matching the stack-up, and this has to be done, of course, in an early and close cooperation between the layouter, the designer, and the board producer. So then we have to decide about the thickness of the flexible layer. We have to ask whether there are mechanical requirements, for example, in that kind that the application needs a very small bending radius, or whether there is a dynamical bending application. This has to be regarded of course. Then we can do a calculation or simulation. That means fit the line width, considering also the minimum width of the conductor. So this is a yield issue and a cost issue, of course. And last but not least, we have to talk about a special option, which is called hedge option for the reference layer. So now we will have a poll, and the question is, which parameter, especially for flex rigid, has to be regarded carefully and has a big impact on the impedance value? So I will now pass over to Mr. Walz.
I would like to take your choice and place your vote in the poll. You have it on your screen right now. I'll wait a moment until the most of you have voted. Okay, 50% of you have voted right now. I'll wait another few seconds. Okay, we are close to 80%. I will close the poll now and show you the results. So as you can see, 0% have voted for copper quality, 0% voted for low dielectric constant epsilon r. 50% of you have voted for thickness of flexible material polyimide, and 50% too have voted for line width. So I'll hand over to Mr. Schilp, and he will discuss with you the results of the poll.
Okay, thank you for your answers. So it's quite interesting. You could not decide really thickness of flexible material, polyimide or line width. Of course, you are right that the line width is very important and has a big effect on the impedance value, but as the question was asked, it's covering the specialty of flex rigid. So for flex rigid, the thickness of the flexible material polyimide has to be regarded, and this has also a very big impact on the impedance value. So the option C, out of my view, is the correct answer in this case. Now let's have a closer look to this effect, thickness of polyimide film. We have done some calculations. The target impedance value was 50 ohms, and the thickness of the polyimide film was variable, and also the separation has varied. So this is the result. We can show you on the right side. You can see the different line width: 100 micron, 125 micron, 150 micron, and on the x-axis we can see the value of the separation between the differential lines, and this is all calculated for polyimide 50 micron. So changing the separation has a not so high effect, but of course the change in the line width has a high effect. But please take care, 100 micron line width has an impact also on the yield, and therefore is expensive in the production for the PCB. So to change, there's no real chance to get an impedance value even with a very fine line width. So the question at that point is, do we really need thicker polyimide to match higher impedance values? And now we come back to the reference layer, the hedge option. And this is a new program which is now available that we can calculate the impedance value also for, with using a hedged reference layer. So this is new in our package, and we have done some different calculation with different polyimide film thicknesses, and showing red 50 micron, which is a standard, 75 micron and 100 micron polyimide thickness. And on the x-axis we can see different crosshatch area of the copper. On the right side 100%, that means fully copper. On the left side 25% of copper area. And we can see that we can find really high values also for 50 micron polyimide thickness if we use the hedge function. Besides the effect of using hedged reference layers is also in that way that it improves the bendability, which is often very important for flex rigid, and also it improves the drying process prior to the soldering process. So these are also two other very important effects. Now there is a special tip for the differential pair design. The small picture showing roughly 20% of copper area. So to improve the return path, the tip is to have the two differential pairs symmetrical to the web knot, so to improve the return path. There is another example showing a very special flex rigid reference layer, so not flex rigid but a flexible reference layer. This is a flexible area of a flex rigid board, and we can see that below the differential pair lines we have 100% copper, but in all the other areas there is a shield opening. So this is also the recommendation of the IPC standard 2223. And again, this improves bendability on the one side, and on the other side it improves the drying process. Now let's have a look on the calculation and the tools we are using. We see here a 14-layer flex-rigid construction with 4 layers in the flexible area, and using a lot of different materials with all the values. This could be documented like you can see here. So there are all the materials in this documentation, all the thicknesses, all the dielectric values, and also the impedance models which are used in the stack-up. So this is quite important to have such a good documentation, that there is no risk to use wrong material in the production or to swap layers by accident. So it's easier to use the correct material, bore thickness, and stack up for the producer. So the next thing is, you can see all the dielectric impedance, all the impedance models and the calculation. You also can see on the right side the wires which are used. So in this case it's only a standard through hole which is used, but it's also possible to use partial wires, blind wires like microwires or buried wires. Now this is the part for the documentation of the flexible area with all the impedance models and the calculations. So this is the complete documentation, which should help to also have a clear documentation in the project and for the product. So now let's come to the possibilities regarding flex-rigid and semi-flex constructions. Surface coplanar could be used if there is no second layer, so no reference layer. So it could be applied for flex-rigid constructions with one flexible layer outside. We call that 1FXRI, as you can see in the middle, and on the bottom side you can see a construction of a FR4 semi-flex construction with, again, one copper layer in the bendable area. Having two copper layers in the flexible area or in the bendable area, we can use a surface microstrip, one reference layer, and this could be applied for flex-rigid with a two-layer flex construction. Could also be applied for a semi-flex with two copper layers, as you can see on the bottom side. So especially for high pin connectors, high-speed signals, this is quite a very interesting option, using semi-flex with two copper layers in the bendable area. If there are even more copper layers in the bending area or in this flexible area, we can also use a strip line model, now with two reference layers. The example shows a stack up of 8 layers, 6 layers of them in the flexible area. On the right side you can see a cross-sectional picture showing this construction. Now the next thing is not only to measure and produce impedance matching PCBs, but also to measure the values, the impedance values with a test coupon. So the reason for using test coupons is mainly to have a good contact, repeatable results, and easy to interpret. There are standard test coupons, like you can see here, using single-ended lines or differential pair. But we can also use specific test coupons, for example, showing flex and rigid flex test coupons, or having smaller test coupons for the integration into a panel frame, for example, which saves a lot of area in the production panel and thus saving money, of course. And the next thing is, with a specific test coupon, we can also use mixed modules on the same test coupon, like you can see here. So this one is a very complex test coupon we have produced. Now what about the measurement equipment? So the used technology is time domain reflectometry. This is a equipment which is produced in Germany, and it's a really high performance equipment. The picture on the right bottom side showing the measurement on a discrete PCB. So it's possible also to measure in a PCB, but as I already mentioned, normally we are using test coupons. And the result is shown in a diagram. So this is small, we make this bigger. So this is the impedance measurement diagram, and we can see the target window, the target value is 100 ohms, and we can see the tolerance plus minus 10%, which is allowed, and the signal, the measurement signal, is a little bit below the target value, but pretty good within the window. The impedance measurement protocol looks like this. So it shows the project, the article number, the customer name, of course, which you cannot see here, and it shows all the measurements. It shows also an immediate decision whether the measurement is okay on the right side, and it shows also the calibration status. So you can see on the right side calibration, yes, or ja, German word, sorry for that. So you can see on the test report immediately that the measurement equipment was calibrated. So now let's have the next and the last poll. So I'm really interested which of the following items is the most important for you. For this poll, I hand over to Mr. Walz.
Thank you, Mr. Schilp. So once again, I want you to vote in the poll, and I give you a few seconds. Okay, nearly 80% of you have voted right now. So 5 more seconds, and then we will look forward to the results. Okay, thank you. So now let's see them. 43% of you have voted for calculation of hedged reference layers. 29% voted for measurement of flex widget and size reduced test coupons, and 29% have voted for calculation in one go and complete documentation. So I'll give back to Mr. Schilp, and he will discuss with you the results again.
So thank you very much for your answers. And I'm really satisfied that we can meet your requirements and now have the possibility to calculate hedged reference layers, which is quite new on the market. And I think this is a good option for the future to meet the impedance requirements and get also impedance matching flex rigid boards. So now we, as we already mentioned, come to the summary. Signal integrity with flex rigid. We have seen that flex rigid technology itself has some system advantages, and but there are at the same time some stack-up constraints which require special actions in design and layout. We learned that we now have an integrative calculation and documentation which helps you also for your project documentation, avoiding some risks. We have learned that now we have the ability of the calculation of hedged reference layers, which is also important for you, as we have learned. And we have seen that the design and measurement of specific flex rigid impedance test coupons with reduced area is possible. So this is the end of the webinar, and I want to thank you very much for your attention. And as already mentioned, we have now the possibility for a question and answer session. So we have got one question which I want to answer at this point. So all the other questions you can find in our FAQ area, or you get the answers personally after the webinar. And the question I want to talk about is a question regarding the transition, the line width at the transition from the rigid to the flexible area. So dependent on the model, dependent on the calculation, the line width will change from the rigid area to the flexible area, and the question is how to design this transition area. Should there be a smooth transition, or could there be an immediate change in the line width? So there are different aspects regarding this question. Regarding the signal behavior, as the signal is really fast, I think the signal will not see a difference whether we have a immediate change in the width or if we have a smooth transition. But regarding the aspect of the production, I would rather recommend to have a smooth transition, and also this helps to have a better feeling at the end. So answer is, please use a smooth transition. The signal will not care about that. So thank you very much for the participation in the webinar, and I'm looking forward to your orders, of course, and also you are invited to ask if you have any questions or project. We would really like to assist you in finding the best solution. Thank you very much.
So I want to point you forwards our little survey. You will be forwarded automatically to it at the end of this webinar. Please take the time to give us feedback on the webinar so we can get better and improve our webinar program. In the survey, you can also tell us your wishes about future topics. After the webinar, we will create a little FAQ and publish it on our website. If your question is not answered at all, you are also welcome to get in touch with us directly. You see the email addresses on your screen right now. Last but not least, I will give you a short overview of our next webinars. On the 7th of October Philip Conrad will talk about chip on board, the small wire bonding 1&1. On 1st of November, Bert Heinz will talk about thermal simulation, helps in selecting the right thermal management concept. Thank you for your participation. Mr. Schilp, thank you for your very interesting talk. And I wish you all the best. Enjoy the time. Goodbye.